Hello and thanks for checking out FasterQuant, automation tools for quant traders. In this video, I'm going to do a deep dive discussion about how the FasterQuant application Edge Test Runner works. The goal of the Edge Test Runner is to find trading strategies whose entry criteria significantly beats random entry and possibly generates alpha. Let's see how it works. First, we have a config file that defines the data and elements the corresponding runner operate on. Next, we have a command prompt pointed to the FasterQuant application project directory, and we execute the .NET run command and pass a relative path to our config file and the run edge test command. Looking at the start and end times of the edge test runner log entries, we can see it took about 7.5 minutes to complete. During that time, it tested 15,670 strategies on our training data set based on 96 strategy condition combinations. Our exit criteria used a range-based stop and limit order that was equal distance to the trade entry price. Of the 15,670 strategies that were tested, 263 strategies passed the strategy filters for our first slice of data, 35 passed the strategy filters for the second slice of data, and 16 strategies passed the filters for the third slice of data. Also note that the last log entry, which indicates there were 0 strategies that had duplicate trades. In the case where there are strategies that have duplicate trades, the strategy with more entry conditions is discarded in favor of the strategy with fewer conditions. The Edge Test Runner output shown here includes the results for each strategy that were tested and passed the filters for each slice of data. The results show various metrics for each trading strategy. Each strategy folder contains the strategy definition, trades, results, and pseudocode of the strategy. Next, let's explore the technical details of the Edge Test Runner. Shown here is the Edge Test config file that was used for the Edge test we just ran. I'm going to describe the properties in this config file and how they are used. Let's start with the strategy condition handler property, which is of interface type iStrategyConditionHandler. Here we can see that it is set to the snapback class contained in the FasterQuant Strategy Conditions plugin project. Let's take a look at the snapback class. Returned from this class are collections of strategy condition configurations which will be later used to generate strategies. The getStrategyConditionConfigurations method takes 2 parameters. The first being a timeframe configuration parameter representing the strategy target timeframe, and a timeframe configuration array representing the higher timeframes used by the strategies. Both of these parameters are defined in our Edge Test config file. Back at our snapback class, here we have a double array strategy condition class which inherits from abstract class strategy condition configuration. This class will build conditions based on the relationship between the MACD and MACD signal data series. Note that the operator is set to dynamic, which indicates that the conditional relationship, for example less than or greater than, will be determined by the actual relationship between the data at the point in time where the strategy is constructed. If we scroll down to the double array strategy condition instance construction shown here, we can see that the operator is less than. This means that the condition is static. This static condition means that when this condition is in a condition combination, the close must actually be less than the lower Bollinger Band before the strategy is built and tested. Scrolling down, we can see that the strategy condition configurations are added to a dictionary containing strategy condition configuration arrays. Let's jump back to the config file real quick and look at the required keys property. We can see that the required keys integer array property contains one element that is the number 4. Looking back at the dictionary in our strategy condition handler code, the required keys value means that any strategy condition configuration combination must contain a condition from dictionary key 4. The strategy condition configuration at dictionary key 4 defines the close being less than the lower Bollinger Band for the first higher time frame configuration that is passed to this method. This approach of having static and dynamic conditions, along with defining required keys, gives us full control over how strategies are constructed, but enables us to leverage machine learning to test a lot of strategies quickly. Let's look at some pseudocode to explore this concept further. Given the following dictionary of dynamic and static strategy condition configurations, with the required keys of 0 and 2, we would have the following combination permutations. No two dictionary array items would be in a combination together. For example, this combination would not be generated. The process flow shown here will be executed against the data series for the target symbol and training symbols defined in our config file. For each combination, and then for each data point in our target symbol data series, if all the static strategy condition configurations are true, then the strategy will be built and tested on the data series of our training symbols. Before covering the remaining properties of the edge test config file, I want to take a moment to show how indicator and other derived data is accessed via FasterQuant. Back at our snapback class, here we can see that this double array strategy condition instance has a Bollinger Bands configuration class instance as one of its constructor properties. Let's take a look at the Bollinger Bands configuration definition. This class implements the iDerived Data Configurator interface, which will enable the SDK to retrieve Bollinger Band data in a usable format, in addition to assist in external platform code generation such as AlgoTerminal. The getData definition method returns information necessary to generate code, and the getDerivedData method calls the actual Bollinger Bands calculate method, which can be found in the FasterQuant indicators project. This product architecture is such that all data processing logic should be at the indicator layer. Back at the config file, let's review what we've covered so far. Our strategy condition handler property, along with the target time frame and higher time frames properties, will handle the retrieval of the dictionary of strategy condition configuration arrays, which, along with the required keys property, will be used to build the strategy condition configuration combination permutations. Those condition combinations will be used to generate strategies based on the target symbol data, and those strategies will first be tested on the training symbols shown here. To elaborate on that, the first date range configuration in the collection will always be tested on the training symbols. All other subsequent date range configurations will be tested on out-of-sample symbols shown here. In this example, our training symbols and out-of-sample symbols are the same, but we will use different date ranges for testing strategies on in and out-of-sample data. In this example, we have one in-sample and two out-of-sample date ranges shown here. Also included with each date range is an optional collection of strategy filters. For example, the first date range has two strategy filters. One for minimum trade count, which is set to 50, and one for minimum win rate, which is set to 65. Only strategies passing those filters will be tested on subsequent date ranges. In a bit, we will use the random trade backtest runner to analyze the filters we are using here. Let's cover the remaining properties of the edge test config file. The trade type enumeration property can either be set to long or short. The limit trades property can be set to true or false. A false value will instruct the backtester to add every signal as a trade for each strategy backtest. A value of true would cause the backtester to prevent the same symbol from being in more than one trade concurrently. The output folder property is a relative path of where the edge test runner output should be written. The order builder handlers property is an array of interface type order builder handler. These two classes will create stop and limit orders, and their logic can be found in the FasterQuant orders plugin project. The exchange trading hours type enumeration can either be set to regular or extended. Let's take a look and see how we define symbol metadata and the exchange. Here we can see the instrument definitions for the symbols that were used in the edge test. And here we can see the regular trading hours and extended trading hours associated with the symbols that we just viewed. Before we conclude this video, let's see how the random trade backtest runner can help to determine if the strategies that were just generated have an actual edge that can beat random entry. Note for the final date range we have a minimum trade count filter set to 100 and a minimum win rate filter set to 65%. Let's test these strategy filters using the random trade backtest runner. Here we have a random trade backtest config file that has the property values such as symbols, target time frame, trade type, limit trades, order builder handlers, and date range, the same as our edge test config file. Also note that the trade quantity property shown here is 100. The quantity percent distribution property is an integer array with values set to 33, 33, and 34. And the test iterations property is set to 5,000. These three properties and their values will direct the random trade backtest runner to run 5,000 backtests where 100 trades are randomly selected for symbols ES, NQ, and YM, and the trade quantities are roughly distributed evenly amongst the symbols. Let's try it out. The random trade backtest runner took just a few minutes to run. Let's take a look at the results. The results shown here show the backtest results for each of the 5,000 random trade backtest runs. Note that each backtest run has 100 trades. Let's sort on win rate. Accounting for the header in this file, we can see that 18 backtests out of 5,000 have a 65% win rate or better. Doing some simple math, we can safely say that given our data set and minimum sample size of 100, all the strategies generated from our edge test will beat random entry at least 99% of the time, as some of the strategies likely have a win rate higher than 65%. That concludes this video tutorial. Please see the other video tutorials at FasterQuant.com to learn more. Thanks for watching.